Alrighty. So now we're on to part 3, which is the last part of the lab. Might be a little bit longer in terms of collecting data and processing the data. This is your directions, and then you're going to go forth and record your data. So this goes back to this thing called refractive index and comparing refractive index. So I'm going to put together this. There's known values. Well, that's the density. There are known values for refractive index on this material. We are going to use, when I go to record it, now you have to watch and you have to record the angles. So we're using a protractor. And some of you might have, flashbacks to geometry and start getting all upset, and it's a tool. This is the tool we're going to use to measure what we need. So we're going to also use a laser pointer. All right. Now, you will notice I'm going to set up the equipment with a dish that has the liquid in it. It's a half Petri dish. Okay, there's 3 types of liquid, and you're spared this. And even if you come in, the material will be long put away. We have clove oil, distilled water, there's nothing in it. It's actually deionized. And vegetable oil. Those are the 3 that we're using. I'm going to take a laser pointer and I'm going to align it and shoot it through the liquid. Refractive index means that the liquid is going to make the material bend. Right? So the laser light will make it bend and you'll have a refractive index for that material. Now, the reason why we're doing this has to do with the fact that glass refracts light. And each type of glass will refract it differently, like each type of liquid. Because technically, glass can be also viewed as this, what's called supercritical liquid. Right? We look at it and we say it's a solid, but it actually has fluidity to it, and it can move on a level that we can't see. All right, so we're going to use data that's in here, sheets that are in here. So we're going to flip past your data tables to this, and this is our refractive index sheet. So I'm going to set it up, and I'm going to have to really kind of work on this because it's hard to do it when you're only one person. You have to hold the laser, and then you have to mark where it comes off, and then you measure. And then that gets recorded in this data table. Okay? This stays constant because I hold it on the same line. Now, all of this is gone by Snell's law. And you may start to tremor when you see Snell's law, but what I'm going to tell you is we're just going to turn it into something that is an algebra, and you solve for x. I will help you with this. That's why you are looking at the directions. If you don't look at the directions, so if you have a friend who says, well, I just skipped those videos, don't help them out. Don't tell them what to do. Make them do what they're supposed to do. Make them watch the video, because that's part of class. Guys, can you tell I'm getting a little frustrated? Like I said, I know this is difficult. This is not easy, but this is what we have, and you need to learn how to cope and deal and do what you're supposed to do. Not go off and say, I'm just going to play my sport and not care. I'm going to travel and not care. Teachers can't travel. By our memorandum of agreement, we leave the state and it's not contiguous. We lose our pay when we have to come back in quarantine. Bet you and your parents didn't know that. Okay, so if we look back, there's Snell's law in here and there's Snell's law in our notebook. It didn't give us the Snell's law here. So I'm going to pull it out of our notebook. So in our notebook, so you know where to go to look, and I have to pull it up. Oh, shoot. For Snell's law, So go back just so you can write it down because we need it. There's these numbers. So refractive index of liquid 1 times the sine of the angle in liquid 1 is going to equal the angle, the index of refraction in medium 2, which we're going to say is air, because the reason why they say that is when it passes out of your little data here, this is air. So we measure the light through air. We measure the light at it. We put the light through the liquid at a particular angle, and then we measure the light through here. And then we measure the angle. So we know what the index of air is. It's well documented, and we're going to use this number. We will find this. We're measuring this angle, and we are calculating this. This never changes, right? Never changes. It's always the same. So we're going to calculate that out. This is going to be the sine of 30 degrees. It never ever changes. So we're going to convert that to a number. This will change, and we're going to figure out, not that, sorry, the angle will change. And we just plug it into our calculator, and then we multiply by this and divide by that. This is the tricky part. You have to know how to plug it into your calculator. Okay, so we are solving for this. So if I need to get that all alone, I have to divide both sides by this value, and it's a function on your calculator. So the thing I'm looking for, which is the different liquids, will be to use your button on your calculator and take the sine of the angle, and I'm going to write down angle because some of you might not know this symbol to mean angle, in the liquid, over the sine of 30 degrees. So I'm going to, oh, my calculator fell on the floor. I forgot. Oh, where did I put it after I picked it up? So I have my calculator, and I'm just going to, I'm clearing out my what's there, and I'm just going to say, okay, here's the sine function. So I'm going to say sine 30 and hit enter. Oh, that does not look right. So I have to look at my mode. I need to go into degree. Okay, sorry about that. So you have to be in your degree mode of your calculator. Okay, so if I do that now I can do sine of 30 because I'm in my degree mode. So I hit sine of 30 and hit enter, and it's, I know this looks funny because I'm in scientific mode, so I'm going to go back to normal mode. Oops, come on. Normal. So if I hit that, it's 0.5. So every time we get a value, we're going to divide by 0.5, and then we have to multiply by 1.0003. And don't forget that, because that little 3 changes the value a lot. Okay? Now, that's one part of the lab that you're doing today. So this is like part 3A, table 4, part 1 of the lab for today. This one is all what we call relative. We are ranking an observation. So you're going to do this, or you're going to watch me do this. I am going to take a piece of the glass, and I'm going to insert it into the liquid. And I'll try to get this filmed as best as possible. I may have to like prop something up. So 3 different liquids: water, veggie oil, and clove oil. And guys, I'm actually going to have to use 3 different types, 3 pieces of glass of each kind of glass, because I don't want to cross-contaminate. Then I'm going to look at the glass above and below the liquid. And you have to decide, does it disappear? Like the lines of the glass, can you see them? You can't see it, you can't see the edges. Okay. Do the edges get bigger? Like, does it enlarge? And then you rank it. A little bit bigger is a 1. A lot bigger is a 5. Okay. A little, a lot. And you have to answer here, this description, what you record here is the number and which way, larger or smaller, for each of these. If it's exactly the same and no change, we record a 0, it disappears. And that gives you a hint about the actual value of how the glass behaves. And then I'm going to continue below. Does it get smaller? Do the edges get sharper and smaller? Again, we're ranking it. 1 is, yeah, a little bit sharper, and 5 is a lot sharper. Okay, way different. So what it means is that the bigger the difference, the less likely or the less like the oil is the glass. Okay, the bigger the difference, the less likely, or the glass is very different than the oil. Okay, by your observations. The bigger the difference, the greater the glass differs from the liquid. So if you know the refractive index of the liquid, which you calculate over here, right? We're going to calculate the refractive index of the liquid here. They even tell you this is what you should get. If the glass has no difference, it's the same value here. If it has a big difference, then it's going to be far away from this. And I will give you insight about, like, if you are bigger, and I got to relook this up, but if you're bigger, your refractive index will be smaller. Okay, so if your edges get bigger, I really need to check this out, guys. Where did I put that? Sorry, guys, it's taking me a while to look this up. I wrote it down. I even have to really think about it because it's physics, about which way it goes. Right. I will tell you, refer to your notes, but remember, if the edges get bigger, I think your refractive index is less. If it gets sharper, it's more. And what I'll say is refer to your notes or refer to class discussion, because I got to look that back up and I really got to make the video right now. So it's really hard for me to figure this out. Hold on just a second. Let me see if I can find my data that I had that tells us what it is. So hold on just a sec. Okay, guys, I did look it up. If it gets bigger, it has a lower refractive index. If it gets smaller, or sharper, it has a higher refractive index. Okay, so that's why you have to say here how much it differs in which way, bigger or smaller, meaning sharper or fatter. You're comparing it above and below the glass. So I'm going to have a little container that's going to have oil in it. I'm going to put the piece of glass in it, and you're going to look and see, does it disappear? Does it go out like this and it looks like it's fat and then it goes back like that? If it gets bigger and it's fat, the refractive index of the glass is less. Okay, bigger than above, then the Ri is less than the liquid. Now this is the hard part. Here are the values for the liquid. If it stays the same and there's no change, and actually it disappears in the liquid, it has to disappear in the liquid, then the glass will equal the liquid. All right. So if you go through everything and you say, all right, Pyrex in veggie oil disappears. I can't see it. I can't see the edges. Then the refractive index for Pyrex equals that of oil. If it, instead of disappearing, if in, I'll just use water. I don't even know what the results are because I don't remember. If it's in water and it gets bigger, I'm going to say it gets smaller. The refractive index has to be greater than water. Okay, if it gets bigger, it has to be less. If it gets bigger in clove oil, it has to be less than clove oil. So you have to estimate, and you're going to estimate between these numbers. You just come up with an estimate based on this. So if it equals it, if I get this, and then it disappears, I would say the refractive index for Pyrex equals 1.474 because that's what vegetable oil is. If it doesn't disappear, I got to figure out what it's closest to. And then say, okay, it's close to it, it doesn't equal it because it doesn't disappear, and then come up with a number. Some of them may be way bigger than clove oil or sharper, I'm sorry, bigger than clove oil. And so it might be higher. Some of them may end up all being, if it's bigger, it's lower. So if they're bigger than clove oil and bigger than water, then it's going to have a refractive index less than water because it says if you give a bigger piece on below than what's on top, you have a lower refractive index. So it's just ranking, but you have to do it this way. Okay. I know you're like, those took a long time, but it's explaining out how to answer.